So a star is a ball of gas that is large enough to initiate hydrogen fusion on its core by itself because of its mass. So that is a star. So how is it different from a planet now? Because a planet would have a rocky core, it won't have a hydrogen core, and it won't, obviously then can't fuse hydrogen. So that's the difference from a planet. You will know a star when you see it, basically. Okay. So now star death. So someone tell me how would you say a star is dead? What is a dead star?
When the fusion reaction stops.
Yes, when the fusion stops, when it stops emitting radioactive smoke. So yeah, that's what a star is. That's what a star dying means. Okay, now to study star death, we need to have a basic idea of what stars are. Everything is better to study if you classify it first. If you know what is what. If you divide it into categories and then you study everything separately. So Arun will be telling you about the HR diagram and how it classifies different stars. Yeah.
So the HR diagram or the Hertzsprung-Russell diagram was formulated by Hertzsprung and Russell. So what they did was they tried to classify stars. I mean they saw a pattern between the surface temperature of a star, which would tell you about its composition, and luminosity, which is how much light it's shedding. And with that, they could classify a star and in the sense of what age it is. You can figure out the age of a star using just the fact, just by knowing its luminosity and its surface temperature. So over here we have something called the main sequence. The main sequence is stars which are still burning hydrogen into helium. They're not fusing heavier elements as of yet. So they're called main sequence stars. For example, the sun is over here. It's a G-type star in terms of surface temperature. And yeah, the hottest stars are classified O, while the second hottest B, A, F, G, K, M. Well, there's a mnemonic for remembering this, which is O, be a fine girl, guy, kiss me.
That's how you remember the series.
You can remember it any way you want to, of course. Yeah. So, and you tend to find the heavier mass stars on the top left. These are also heavy mass stars, but they're not of the main sequence. And you find the lighter stars over here. Brown dwarfs, red dwarfs, yellow dwarfs, and so on. Yeah. I'm going to talk about very low mass stars, which are...
I am.
You are?
Yeah, then you talk about low mass. I talk about high mass.
Yeah, Amartya was going to talk about very low mass stars.
Yeah, thank you. Anyway, so now first we're going to talk about very low mass stars. Now, they don't get as much love as the other stars for some reason. When you look online, you don't find much information. But anyway, these are very low mass stars. They are also called red dwarfs. They are the only ones that are called red dwarfs. Their mass is less than 0.4 solar masses. If there's a ball of gas that is less than 0.08 solar masses, it cannot start hydrogen fusion. It's called a brown dwarf. You can't classify it as a planet or a star. You call it a planet, it doesn't matter so much, the distinctions aren't that strict. Anyway, so between 0.08 to 0.4 you will have a red dwarf. So it consists of a core and a convective layer. A core is in the center. It's basically going to be more dense because there's everything just squishing down on top of it. There's a lot of gas over there. So the entire thing is going to squish on top of it, and that is a core, and this is where the hydrogen fusion will occur. And the important thing here is, in a red dwarf, there's no distinction between the core and the convective layer. The convective layer is everything surrounding the core, because it's not dense enough to fuse hydrogen. So, So anyway, the convective layer is where the heat from the core escapes. Now there is nothing between the core and the convective layer. Therefore, any hydrogen that fuses into helium, so any hydrogen that fuses into helium in the core will circulate out of the core and go into the convective layer, and from the convective layer it will come back if it needs to. Otherwise, there will be more hydrogen coming around from the convective layer. The entire thing will circulate, and there will be, the entire hydrogen will be used up as fuel inside the core. Yeah, so life expectancy, the universe isn't old enough for any of these stars to go out yet, because they've got so much hydrogen to burn. And the thing is, they're pretty small, so there's not much pressure at the core, therefore the fusion rate is lower. So, yeah, actually, So yeah, death of them, I mean, we don't know yet. They haven't died yet. We won't be there to see it if they do. But anyway, once it occurs when all the hydrogen is exhausted, all of the hydrogen, because it's going to be replaced by helium, and the convective layer of the hydrogen is going to come back into the core. So helium is more massive than hydrogen, obviously. What happens, like it's gas laws, the center of the core will act as an ideal gas. More mass means more pressure, means higher temperatures. The star will be higher temperature. Once it's burned all its hydrogen, it will glow white. It will glow blindingly white. That's called a white dwarf. So after that, it's going to cool. No, wait, one second. Yeah, it turns into a blue. It turns blue first, then it goes white. Then it goes white. And this is composed of helium, so it's a helium white dwarf. Then it's going to cool over billions of years again. It's going to cool into a dead black dwarf. Yeah, we can't see any yet. The universe isn't old enough yet. So that's what happens to very low mass stars. But once the mass exceeds 0.3 sun mass, then we have low mass stars. And yeah, we've seen them die, we know what happens. So Arun will explain that.
Yeah. Low mass stars are basically stars which are greater than, you can say, 0.4 solar masses, and let's say lesser than 8 solar masses, because stars...
I didn't explain how much is the solar mass.
It's the mass of the sun. So, yeah.
Sure?
Yeah, okay. So, and I mean, stars above 8 solar masses actually die in a different way, so you can actually classify them with this scale. Yeah, so low mass stars are stars like the sun, basically. And see, he said that very low mass stars just have two layers, basically the core and a convective layer. And the convective layer moves freely and can interact with the core. In these heavier mass stars, there is an extra layer that comes in between because of the mass, which you would call the radiative layer. So the core does not interact directly with the convective layer. The core is what's fusing hydrogen into helium. And typical stars like the sun, low mass stars like the sun are expected to live for around 12 billion years. So you could say the sun is approaching around middle age because it's like around 5 billion years old. Yeah, basically this is the, this is a differential, so to speak, of the star. You have a core, but you have a radiation zone so the fusion occurring in the core does not interact with the convection zone. Of course, there is more to talk about this star, low mass stars, but I'm just going to be talking about death. The process of death, it starts when the hydrogen in the core is exhausted. From here onwards, you know that the star is dying. In the sense, there is less of fuel to burn, and it's a one-way cycle. The core contracts because because helium is more massive and the core gets hotter. In low mass stars, because there's nothing to expand, in the sense the convective in very low mass stars there's nothing to nothing expands because the convective layer and the core are basically interacting with each other. So it turns blue as it gets hotter. In this case, as it gets hotter, the heat spreads out and the outer layers expand. And you get what you call a subgiant, which is around 10 to 20, the size of 10 to 20 suns. And after the core is again, still contracting, still burning hydrogen into helium, and the core heats up more. Because of this, the shell hydrogen fusion, meaning the hydrogen shell that's outside the core, meaning in the core you have hydrogen converting to helium, in the radiative zone you have just hydrogen, but now even this is getting heated up. Because of this, there's more heat produced, and even the outer shell hydrogen starts fusing into helium. Because of this, even more heat. And again, the outer layers, because of this, expand even more, and you get what you call a red giant. A red giant, basically, you can see this is like the orbit of Venus. You expect the red giant to be around this size. It's also expected the red giant could be like the size of one astronomical unit, basically, touching Earth. If this was the sun. And this would take place around 12 billion years from the star's conception. Yeah, right now the core becomes degenerate. We'll talk about degenerate very soon. And right now the core is so hot that the helium in the core can also initiate fusion. Yeah, so you get what you call a helium flash. Helium flash occurs when degenerate helium, we'll talk about that soon. Again. Degenerate helium fuses rapidly into carbon in a few seconds. Not all of it, but a large portion of it. This releases a lot of energy. And now because of this, the core expands slightly because the helium goes from degenerate to a regular, almost ideal state. And yeah, star enters a horizontal branch in the HR diagram, which I'll show you soon. The luminosity decreases, meaning the star was first, it's a red giant, it's expending more energy. Right now, the star shrinks because the energy is absorbed by the core after the helium flash.
And the helium flash follows the triple alpha process.
The triple alpha process is where helium forms some carbon and maybe even some oxygen by fusion. Yeah. To sum it up, basically a star like the sun would be around here in the HR diagram. You could say, when it becomes a red giant, it moves up, so to speak. Its luminosity increases, but because its size is that much bigger, the surface temperature is a bit lower. So, even though its luminosity is higher, the surface temperature goes down. And after that, it enters a horizontal branch because of helium flash. Now helium is starting to fuse into carbon, and over time the helium core again, even this gets depleted in the sense it's becoming carbon. But carbon fusion cannot take place because carbon fusion requires temperatures around 500 million degrees Celsius, and it's not hot enough in the sun yet. And it doesn't happen for the sun. Yeah. And there's a shell of helium around the carbon, there's a shell of hydrogen around the helium. And now the carbon, because carbon is denser than helium as well, even the helium starts getting hotter because the denser gas is hotter and this spreads to the outer layers. And because of this, again, the helium outside starts fusing into carbon, and this again, the heat again is transferred to the outer shells, and you get what you call a second red giant stage. And this will take a million years more after the 12 billion.
And this will be
Yeah, but the core is never hot enough for carbon fusion, and helium fusion occurs again in flashes here in the outer shell. Because of this, when the sun becomes a red giant in the beginning, it loses some of its mass because as it's much bigger, the gravitational force to pull it is much smaller. It loses around a third of its mass. And here when it becomes a second red giant stage, it loses half of its mass, half of what's left. And helium fusion again occurs in flashes, and because of this, again, like sudden eruptions of energy take place. You'd call them paroxysms, right? And because of that, even more mass of the outer layers is lost. The sun is losing mass at a really fast rate. The outer layers are completely lost, and you could get what you call a planetary nebula for some stars. But the naked core that's left behind, you would call this a carbon-oxygen white dwarf, or simply a white dwarf. In this picture, we show you Sirius. You can see that night, even tonight. It would be called the brightest star of the sky. It's actually a binary star system accompanied by what? Sirius B. So in visible light spectra, this is what you would see. Sirius is much brighter than the white dwarf next to it. Now, Amartya will yeah, I'll talk about white dwarfs. But now white dwarfs primarily emit light in X-rays or higher emission spectrum. So this is what you would see when you would observe the white dwarf in X-rays. Sirius doesn't appear so bright. This is the white dwarf next to it. So a white dwarf, depending on different types of composition, in very low mass stars, a white dwarf would be primarily composed of helium. In this case, the white dwarf is composed of carbon, oxygen, sometimes neon even. And the limiting mass for a white dwarf, meaning a white dwarf is held together by what you call electron degeneracy pressure. Have you guys learned of the Pauli exclusion principle? Tell me what it is.
Okay, it's one of the ways in which you fill the orbitals.
No electrons that are
The number of electrons can have the same quantum numbers. To define it another way, instead of using quantum numbers, you'd say that no two electrons can occupy the same space and have the same momentum. Yeah, but there is a limit to a white dwarf above which it will collapse under its own gravity. This, I mean, 1.4. If the white dwarf itself is 1.4 times the solar mass, that's called a Chandrasekhar limit. Yeah, so basically Chandrasekhar around 1930 or something, he thought what happened to a white dwarf if it became heavy enough that maybe even gravity can't support its electron degeneracy pressure. So I mean he was 19 at the time, of course, when he calculated it. Yeah, above 1.4 solar masses, a white dwarf would collapse further into other stellar remnants. And white dwarfs generally cool over billions of years until they form what you call a black dwarf, or they turn off, so to speak. They're still emitting light because the light inside the dwarf inside the star during fusion is still not escaped yet. And white dwarfs also come with planetary nebulae most of the time. But the sun may not form a planetary nebula. This, for example, is the Dumble Nebula, which you can observe, I believe, in Taurus or in constellation Taurus, if I'm not mistaken. I think I'm wrong. Yeah, so the gas that escaped the star could be lit up by the white dwarf in the center, right? I guess this is a white dwarf in the center. So the gas that gets lit up by the star can get ionized, and because of this, during process you call electron recombination, the gas glows as well. You'd call this a planetary nebula. And I mean the effect is called fluorescence. And based on the color of the planetary nebula, for example, we know that oxygen basically is kind of green or sometimes blue. Based on the composition of the planetary nebula, you can actually find out more about the star that caused it. And the planetary nebula generally, they only last around 1,000 years, meaning these things are kind of rare because they last quite a short time, after which they just dissipate because they're too far away from the white dwarf. Yeah, now I'm going to talk about high mass stars. What happens to stars which are greater than 8 solar masses?
So yeah, that was low mass stars after very low. Now we come to high mass stars, which are greater than 8 solar masses. Now the thing here is, they are much more massive, the core pressure is obviously higher, there's more mass, pushing down onto the core, there's much more stuff going on. So at the core the pressure is much higher, therefore fusion is going to occur much faster. Fusion is going to occur much faster because they're going to collide faster, because there's less space to move around, that's physics. So they're going to deplete their hydrogen fuel a lot quicker, really quicker. The bigger the stars are, the faster they'll run, and that's why you don't see too many large B sequence stars. We don't see so many of them.
There's Beetle guys.
Yeah.
Beetle Joes, how we want to pronounce it.
Typical Jones.
Is that a pronounce it?
That's original Arabic, but that's okay. No, anyway, so this life expectancy is less than 100 million years. It's not going to live long. It's not going to live longer than that, but it's going to go up with it. Anyway, then we have the depth of a thing. So they're going to go through the same thing as before, as a low mass star, they're going to go through the same cycles. So it's going to turn into a red super giant. Red giant's not big enough, not a big word, it's not big enough. Yeah, this right here is Betelgeuse, it's a red super giant. There's the size of the star, there's the size of the Earth's orbit. It's massive.
Size of Earth's orbit, just say.
Huh?
Size of Earth's orbit.
The size of Earth's orbit. It's not a size, it won't even, how small a pixel do you want to show?
You can't see Earth, even one pixel.
Not even one pixel. Anyway, to start with, they turn into a red supergiant. So, so carbon, now what built up in the low mass star was carbon. It cannot fuse carbon. But this star is bigger, it has more mass, it has more pressure, so it can. It will fuse carbon, it's going to fuse into neon, magnesium and oxygen. And for some stars with less than 10 solar masses, this is when it's going to expand again and lose its mass. Like for carbon, low mass stars, they lost all of their mass, and the white dwarf stuff, right? So over here, it's going to lose its mass here and it's going to form a neon white dwarf. This doesn't happen as much either. But if its mass is more than this, then it can fuse neon. If it cannot fuse neon, it's a neon white dwarf. If it can fuse neon, we go ahead. And higher mass stars will fuse neon into magnesium and oxygen, and it's going to grow again. Basically, whenever a new fusion starts, the red giant from before collapses back, and whenever the fuel runs out, it expands again. Because the same thing is happening again and again. Because whenever the fuel is going to run out, the coal is going to be more dense, it's going to get hotter, it's going to expand the gas, it's going to blow up. Then when the temperature finally reaches a critical point, it's going to start fusing again. The coal will start absorbing most of the heat it's producing. The coal is going to expand again. The outer layer is going to contract again. So these are several oscillations. Yeah, we call them oscillation. Red supergiant to blue supergiant. Because even when they're contracted, they're still going to be really bright. So they're going to be blue. They're going to be blue, red, blue, several times. So oxygen is going to fuse into silicon. Silicon is going to fuse into iron. This is where the trouble starts, I'll tell you. Anyway, this is the sun, pretty much. This is Sirius, and this right here is a blue supergiant region, the left foot of Orion. So yeah, yes, this is how big it is. So yeah, anyway, this is the constellation of Orion. Over here we have the red supergiant Betelgeuse.
They come out at night and midnight.
Yeah, everything.
Very clearly.
Yeah.
And sometimes you can even see that Betelgeuse is red.
It's very clearly red.
It's pretty really red. I mean, what is red? Anyway, so this right here is region. It's a blue supergiant. Okay, now, can some of you guys name the other stars?
Regulus.
No, she did not. Okay, other than
This one is Regulus, right?
Yeah, Regulus is a
Regulus is over there somewhere. Regulus is in part of the great dog. No, sorry, it's part of Leo. Regulus is part of Leo. It's in the other side of the scale. You guys know the other stars? Anyone?
Yeah, I remember.
Okay, can name the belt at least. They are very vague names. The three stars.
yeah, Arabic.
Yeah, I mean, everything is Arabic. Betelgeuse is Betelgeuse, that's also Arabic. So anyway, come on. No? Okay, Shane.
Okay, so the one of the belt, one is Al-Nilam.
Al-Nita.
Al-Nita. I can't pronounce anything, it's well not for you. Then Al something else.
Jalam.
No, it's sure. I mean, I'm not
Okay, so we memorize this, so.
Yeah.
I mean,
Are they the ones that align with the three pyramids? There
No,
are three
those are
stars
planets.
in the sun.
Those are planets.
There are three stars in the sky that align perfectly with the three pyramids which are in Egypt at some time of the year. So
no, I mean the photo that's going on 9 and stuff recently, those are the three planets. No, not that. Right?
not that, it is yet to be full.
No, but this belt is too
They
small.
saw
I'm not
that.
sure if this is it.
Like if you're looking at the pyramids from one side, like each pyramid, and then you see the three stars. It's one of those three, right?
Not always.
No, in very special situations.
So, since they have actually names of this
They're not
one.
bad.
I mean, most stars in the night sky have Arabic names because, like, during the, I'm not sure which year, like, a lot of scientists around in the, in the Middle East, so to speak, people were into science and stuff, they named the stars.
Golden age
So
of
actually the Middle East was the powers of science and
Yeah,
back in the day.
dark age of Europe, right?
Yeah, really, it was
Right. It was a brilliant time for science and stuff. I mean,
Can you name the three stars?
yeah, I mean, I'll tell you what I know. This is Bellatrix.
Yeah.
This is Seth. These are Al-Nilam, Al-Nitaq, Al-Nilam, Mintaka. And this is the Orion Nebula. There's a process of active star formation. Like these are seriously bright. They're extremely new stars. They're like new blue. They're blue supergiant stars. Like they're being formed right now. Why are you laughing?
Oh, I remember it in the Harry Potter names. That's why I thought one of my.
Yeah, everyone's like Bellatrix. Yeah.
That's why I actually remember. That's why I thought.
The serious also on the other side. They're pretty fun. Yeah. So anyway, this is Orion. So we gave you two examples in one constellation. So now we continue. Oh yeah.
This is
VY minus
the largest known star.
This is the largest known star. It's a red hypergiant. This right here is the sun. Yep. And this is Earth's orbit. Here. And this is the largest known star. They're pretty small.
And a hypergiant, stars like these, you expect them to, go supernova. And the hypergiants, they go.
Hyper.
Oh, nice.
Yeah, pretty much. And so this is a supergiant star. So what I said about build-ups and stuff, right? So what's going on is same. layers, like the low mass stars, like an onion. What's going to happen is that outermost layer is going to start fusing hydrogen. The layer under that is going to fuse helium, under that carbon, neon, oxygen, silicon, and iron core, basically. So, I mean, at different things are at different temperatures, so they will fuse different things. Because, yeah, the center heats up, it initiates in the next one. The center hits up the next time, it initiates here, it initiates here. So, it's cascading outwards. Helium, hydrogen, helium, carbon, neon, oxygen, silicon, and iron. And all hell breaks loose when we get to iron.
Yeah, you
Takes 100 million.
Huh?
How much time does it fuse?
Oh, yeah. So, yeah, hydrogen fusing in 100 billion years.
I know. 100 million.
100 billion, sorry. Yeah, the hydrogen fusing into helium will take 100 million years. The helium fusing into carbon,
10 million years. 1 million.
the lifetime of the star is 100 billion.
Yes, it's 1 million for 20 solar masses.
Yeah. Oh yeah, 1 million for 20 solar masses. Helium is gonna fuse into carbon for how long was it?
Around half, less than that, 50,000.
Yeah, 50,000 years. So carbon is gonna fuse into neon over 1,000 years. 1,000 years. 1,000 years, let's go. And neon is gonna fuse into oxygen over a few months.
What?
Yeah. All of the neon is going to fuse into all of the oxygen in a few months. It is that hot.
It's a few months, isn't it?
No, man, that's a few weeks.
Okay.
And a few months, technically a few weeks is a few months, but that's okay. So oxygen is going to fuse into silicon in a few weeks. I don't know.
One day ask.
That escalated.
All of it.
Wait, all the silicon into iron one day.
One day.
And what's the lifetime of the whole stuff?
Huh? 100 million years?
Not 100, that's for the lower mass stars. This one would be, I guess, it's atom.
Yeah, go on.
I mean, these are really massive stars, so you know, they live much shorter.
Much more.
Yeah, around 1 billion.
Not even a billion.
Not a billion, no one near a billion.
The one before this was 100 million.
Yeah.
So this will get around 1 billion.
I mean, human perception of large numbers is really, bad. Because yeah, you think like you just spout numbers like a billion, trillion. The thing is, a billion is so much larger than 100 million. 100 million is much larger than 10 million. So the orders of magnitudes change everything. A lot of things. And perception isn't enough for that.
I'll tell you, there was, I don't know if you're seeing, there's this recent video about numbers where he says that it take you, if you want to start counting 1, 2, 3, 4, say one number per second, it will take you a few weeks to count till 1 million, and it will take you 32 years to count till 34 years to count till a billion.
So you can never count to a trillion, basically.
No,
If you go like 10 numbers a second.
Yeah.
If you go 1,000 numbers a second, it take you 34 years. So,
Exactly.
exactly, so you can't do this.
So this happened, right? Silicon fused into iron in one day, right? So that's not good for anything, right? So the problem here is silicon fusion into iron is endothermic. Everything else was exothermic. Everything else was releasing energy. Iron fusion is endothermic. So
It won't fuse further.
huh?
It won't fuse further.
It won't fuse further. Yeah.
it absorbs energy.
Yeah, it absorbs energy. It won't fuse further on its own, yes. But it will absorb energy and fuse further, but we can't do it. So stars heavier will come here by fission. They tend to come towards iron and lead. Stars lighter tend to come towards iron and lead. You guys want to know why? You don't have to. It's about strong nuclear forces. That's pretty much it. So electron degeneracy pressure is not enough to counter gravitational force at this point. Because iron, it's happened really fast. It's happened really, and it's absorbed a lot of energy. And so degeneracy pressure states that to counter the gravitational collapse that's happening right now, the electrons have to move faster than the speed of light. So that's not going to happen. So, yeah, right.
In the center, you have what you could call an iron white dwarf.
Yeah.
But
Basically, you have an iron white dwarf now.
as it's forming, it reaches it reaches a Chandrasekhar limit, and then it exceeds that as well.
Yeah, it exceeds that. So my iron white dwarf won't form. So it's going to collapse. So this collapse will cause a shock wave called a type 2 supernova. Yeah. Yeah,
This happens in a few seconds, basically.
in a few seconds, the entire star is gonna blow up. Do I have it in the next step? What happens? Yeah. At densities this high, I mean at the center of the star right now, the electrons and protons are going to combine to form neutrons and neutrinos. So this is a quantum physics phenomenon that's going to affect a star that big. I mean, it's extremely, it's mind-boggling, but yeah. So they're going to combine to form neutrons and neutrinos. So there's a colossal number of neutrinos are going to get released, and they're carrying off an enormous amount of energy. Now they don't react very well with normal matter, neutrinos, but there are a lot of them here and they're carrying a lot of energy. So the core is collapsing, is free falling, it's collapsing seriously fast. So the core collapse causes a shock wave that comes outwards, and this hits the incoming gases because everything is collapsing around it. The core is collapsing faster, it creates a shock wave that hits the outer collapsing waves. And this will cause the entire thing to come nearly to a halt. Then the neutrinos are going to slam into it. Yeah, it is literally an explosion of a star. So yeah, this is a documented picture of a supernova, like 1987, I think. So this was a star, and this is a supernova. You can see it across the galaxy. It has so much energy.
You can see supernovae of other galaxies as well. They're basically some of the brightest objects in the
So yeah, the energy produced by a supernova, right, is basically like
the energy produced by the neutrinos, which slam into the outermost incoming gas.
Yeah, it's like
Is around 100 times the sun's energy that the sun would produce in its entire lifetime.
in its entire lifetime, 100 times that, just like that. Yeah, supernova. They're gonna blast out at 0.1 C, 10% the speed of light, the gases. So energy from supernova, I mean, it is so energetic that iron fusion will occur in the gases surrounding it. So iron will fuse into heavier elements like uranium and lead and the heavier
Anything heavier than iron.
Anything heavier than iron. So yeah, this is called explosive nucleosynthesis. Tell me that term is awesome. Come on. Explosive nucleosynthesis. Yeah. So yeah, the layers will collide with the other active star-forming nebulae. This will cause chain reaction. So this gases from this nebula will go into another star-forming nebula and it may become part of another star.
I mean, we won't have heavier elements above iron here on Earth or in our solar system if not for maybe another supernova, whose material collided with our star-forming nebula.
So all the heavier elements we have in our solar system and on Earth, everywhere around us, is because another star that went supernova probably a billion years ago. Right, so this line gets cheesy really fast, yeah, but we are all stardust, right?
Yeah.
Yeah, very good, yeah.
The sun produces helium at height. And there's
then the core is carbon,
everything else is from somewhere else.
Yeah, everything else, every single atom of phosphorus in every single part of your DNA, every single iron nucleus in all of your blood, every calcium atom in all of your bone is from some star. Absolutely. Nowhere else. It can come from anywhere else. Yeah, she's interesting. So this is called the residue, right? And this is the center is what remains. Yeah. So this is called the residue. It's called the supernova. So we have an excuse to put a bigger picture of a supernova. So why not? This is probably a neutron star. Hopefully, there's a neutron star. So the supernova. There's the entire residue. So we have hydrogen glowing red and oxygen glowing blue, and we can tell a lot from this too. So
you can see the layers. You can see the layers as you go in.
Yeah, you can see the layers as you go in. Okay, now Arun will cover the remaining. So here's a table summarizing things. So less than 0.08 mass of sun, brown dwarf. The final size will be 10 to the power 5 kilometers. I mean, they're not stars. They're not going to fuse anything. They're never going to fuse anything. So then we have helium white dwarfs, 0.08 to 0.4. They're going to keep, they're going to keep some of their mass, but it's not going to be much. And yeah, they're going to keep all of them mass. What am I talking about? Yeah, they don't lose any. I mean, they're very low mass. They don't lose any of their mass. They're going to keep all of their mass, and their final size will be more or less the same as what it was before.
The only way they lose mass is by radiation of sunlight, by which they're losing energy, which is mass.
Yeah, we get it. So, the 0.4 mass to 8 mass sun, they're white dwarf carbon white dwarfs, they're carbon white dwarfs. So the final mass will be less than 1.4 mass of the sun. And the final size will be 7,000 kilometers, and the density is around 10 raised to 9 kilograms per meter cube. 10 raised to 9 kilograms of meter
You
cube
can say 1 ton per centimeter cube, so centimeter cube.
is 1 Dyson.
Weighs
1
1
ton.
metric ton.
Huh?
Yeah, weighs 1 metric ton.
Yeah, it weighs 1 metric ton, this one dice. That is white dwarf material. Yeah, I mean,
Neutron stars are much denser.
That's fun.
And you can see the our order of powers of magnitude over here, 10 power 9 and 10 power 18. You would think it's
yeah, 10
don't
power 9 to
confuse
10
it as, factor of 2.
Yeah, but it's, yeah. So yeah, I mean, above this we have the neon white dwarfs and stuff like that. So, but making a blanket of the whole thing, we have 8 to 20, the cores of these stars will form neutron stars. 8 to 20 solar masses. The final mass left over will be 3 to 4 times the mass of the sun. This is the limiting factor for the, less than 3 to 4 times the mass of the sun. This is the limiting factor for neutron star cores. The final size will be 10 to 20 kilometers. And check this out. This is gonna be the size of the core after this. And yeah, this density, yeah, pretty much. Yeah, we have a neutron star side after this. We're not going to talk about neutron stars and black holes so much because they're not part of stardust per se, and you guys are going to do a thing on pulsars anyway, right? So, not pulsars?
Quasars.
But not
But
pulsars.
then if you're going into quasar, then we can just
Combine the two.
pulsar as well, because see, quasars are to do with black hole, pulsars are to do with...
No, I mean, if you guys want to cover it, we'll talk about it more right now. If that's okay with you, that's already
Yeah, where's Madhav?
I'm here.
So you're going to talk about quasars and pulsars and quasars, all will you do all?
Okay, I think we can do all three.
Because if you take up one, you can do...
Yeah.
You can briefly...
You can fit it
Quasars are distant galaxies which emit so much energy in gamma rays.
You can do it in brief right now. We'll do a much more detailed version.
Yeah, we won't say what a pulsar is. We won't give spoilers.
No, you can say what pulsar is.
Same.
And then don't say more about pulsar.
Okay, fine. Okay. Yeah, neutron stars and then black holes. Greater than 20 mass of the sun, original size. Final mass, we don't know. Final size, assumed to be 2.75 kilometers. Yeah, pretty much. Density, not happening. No. So yeah, this was, now we can talk about neutron stars and black holes.
Neutron stars are one of the possible stellar remnants other than white dwarfs. I mean, there are the theoretical stellar remnants as well called quark stars. You don't know if they exist or not. Neutrons are basically held in place by what you call neutron degeneracy pressure, which basically electron degeneracy pressure, but neutrons again now they can't occupy the same position in space and have the same momentum. So because of this, neutron stars are held together, meaning this, what do you say? This goes against gravity, and this is what keeps it, intact. And neutron stars generally rotate very fast because, you could see, it's a simple physics problem. Keep decreasing the radius of a sphere, rotating sphere, you see that it's with omega, when omega keeps increasing radial velocity. Yeah. So, the fastest known neutron stars can spin around 30 times a second. And they emit light and mostly X-rays. And because they, intense energy, a lot of energy because, they're so packed together that they have a huge magnetic field. Neutron stars are, the magnetic field, one second. The magnetic field is so intense that sometimes neutron stars have,
No, wait. Talk about the composition first.
Yeah, neutron stars are basically composed of what you call neutronium or just neutrons. So, they're packed together. And, their density again, as you saw, was 10 to the 18 kg per meter cube. How this comes to be is because, in a typical atom, you'd say that 99% of it is empty space. In the sense, you have a neutron, around 99% empty space, another neutron in packed atoms.
Like if you expanded an atom to like 100 meters, the nucleus would be the size of a marble in there.
Yeah. So in a neutron star, all the neutrons are close together, they're packed. You don't need to go to 99% of an atom to find the next neutron, they're packed.
So I mean the first marble, then you walk 100 meters, then you walk another 100 meters, there's another marble.
That's the normal.
That's a normal
That's
atom.
normal atom.
And over here you have a marble and then you have a marble.
Yeah, many.
Yeah.
So basically for a neutron star, normal matter is polluted vacuum. You understand how it works? Like,
Wait, what?
for it, it's empty. You put a neutron star, you release it like that, it's going to go through.
Yeah.
It's just going to go through.
Yeah. Yeah, I mean the neutron star is like, it's much heavier than the sun, and it's like, 10 kilometers or 20 kilometers in radius. Or is it diameter?
Huh?
Yeah, radius, I guess.
Yeah, man.
And now if the neutron star is, neutron stars are some of the most magnetic objects in the universe. Sometimes some neutron stars are so magnetic, they're given the name magnetars, right? Because of the spin and the magnetic field. Oh yeah, and neutron stars have like around like a few meters of crust with like regular matter, like all squished together. And because of rotation, you could have what do you call a star quake, right? A star quake is basically, the few centimeters of crust, colliding with another, getting on top of the other.
Like an earthquake would have a tectonic plate hitting another tectonic plate. There'll be a difference of around like few kilometers. In a star quake, there'll be a few centimeters of the crust. Yeah.
I mean, I won't give you all the details, I guess, but like, in the video I watched, they said that in 2004, a satellite observing in X-rays was temporarily blinded by a flash of X-rays. And it was not even coming from the direction it was pointing at, apparently the other side. And it temporarily blinded the satellite. And they said that the force was powerful enough to compress our Earth's magnetic field to a certain amount, really tiny.
And ionize our upper atmosphere a bit.
Yeah. And this was located to the source. The source was located to a magnetar around 50,000 light years away.
A space quake, 50,000 light years away, its crust shifted by 1 centimeter.
Yeah.
That's basically what happened to blind one of our X-ray satellites.
But apparently, magnetars are really rare. So, if a magnetar was much closer, bad for us. And black holes. Basically, what happens if the core of before the star goes supernova, if the core at the iron core is larger than 3 solar masses, meaning even neutron degeneracy pressure cannot stop its collapse. Yeah, and you'd say there's nothing that stops gravity from collapsing the star, and you get what you call a singularity. You call this event a black hole. The radiation event horizon. To talk more about, do I explain more about black holes?
Yeah, what is singularity exactly? In Interstellar, they explained that term 100 times. Singularity, what is it exactly?
To put it in like a really, it's not like I know everything about it, but to put it in easy, simple terms, it's basically a point with infinite density.
Okay.
To put it in space-time terms, general relativity or something, it's a point with infinite curvature. Meaning all the paths that an object can take will be directed inwards at that point. Meaning nothing escapes.
Not even light.
Light cannot escape what do you call the event horizon. And black holes are so massive that they have something even you call a photon sphere, which is basically, a planet orbits a sun, that's light orbiting a black hole.
Don't smiling. Oh, okay, that's interesting.
Spoilers for the next section.
Yeah.
Alright, okay, those are spoilers. Yeah, that concludes black holes.
Right.
Okay, no, black holes is a topic in itself, right? So, we won't talk about too much.
Yeah, so to summarize, stars are formed basically in star-forming nebulae, which are basically just gas, which is, floating around. From there you can go one way to a very low mass star, not mentioned here.
Yeah, very low mass stars don't get any love.
they become, you know, red dwarfs, then probably blue dwarfs, then a white dwarf, and a white dwarf eventually becomes a black dwarf, which is when it shuts down. I mean, turns off, so to speak. I mean, otherwise, low mass stars, you know, you get something like, for example, the sun. The sun will go through a red giant phase. I mean, goes to a subgiant, then a red giant, then collapses slightly, again becomes a second red giant, collapses further. I mean, no, and now all the gas is lost, and you get a planetary nebula and a white dwarf. And for heavier stars, these are called blue giants, not blue. Don't confuse with blue supergiants, which is a step in its death. So blue giants, for example, a star called Spica, I guess, in Virgo. Yeah, these form red supergiants, or even red hypergiants for really massive stars. And you know, they go red supergiant, blue supergiant a couple times, you know, for every fusion, hydrogen into helium, into carbon, into oxygen, I mean, the neon, into magnesium and oxygen, into silicon, into iron. And I mean, this goes to supernova. And from a supernova, depending on the mass of the core, you could either get a neutron star or a black hole. And yeah. And there are other theoretical particles you call a quark star. Apparently, quark degeneracy pressure keeps it together. I mean, it's theoretical, I think. And there are other types of stars as well, theoretical, so we're not talking about it. Yeah, this concludes our presentation on stars.